Hello, my name is William Forsyth, a data science graduate student at Regis University. This video is a presentation of my Practicum 1 CNN image classification project. I chose this type of project to get a better understanding of deep learning image classification. This project is one stepping stone among perhaps many to fill technical and knowledge gaps on a path to potentially contribute to and help advance early and accurate skin cancer detection and identification. Skin cancer is a deadly disease. 18,000 people in the U.S. die from skin cancer each year. Early and accurate identification is paramount. In this video presentation, I will be tackling a very important question. How well will this deep neural network model classify skin cancer using the HAM10000 data? More precisely, how well does this CNN model correctly separate the cancer images from a broad selection of skin lesions? The three main objectives for this project involves building a Keras Sequential image classification model. They include 1. To significantly reduce or eliminate overfitting. 2. Attain at least an 80% test accuracy without violating the first objective. And 3. Build a model that can work with limited resources while attaining the second objective. The major problem is that the data is heavily biased in favor of a single class of 7. Because of the imbalance and a focus on a minority class, specifically melanoma, we will also be looking at the macro average in the classification report. I just want to run this by real quick. The model build type is Keras Sequential CNN image classification using TensorFlow backend. A GTX 1070 GPU with 6.1 gigabytes of available compute memory was used to run the models. The data used for this project was a collection of 10,015 dermoscopic color images sized at 600 by 450 pixels. Dermoscopic imaging produces moderately low noise levels and relatively uniform background illumination. The images had been previously cropped and centered. That's not to be confused with pixel centering. The variable cell type is a target variable that included 7 types of skin lesions. Those would be actinic keratosis, basal cell carcinoma, benign keratosis-like lesions, dermatofibroma, melanoma, melanocytic nevi, and vascular lesions. This list of process steps are necessary prior to performing exploratory data analysis, image resizing, and image classification pre-processing. So I'll just skip the details and we'll move on to the good stuff. To build the CNN model, we need only the target variable and the images mapped to the image path. Although exploratory data analysis was wide-ranging, the primary consideration was for the relative differences between cell type counts. The cell type count graph shown revealed that the data was highly imbalanced, with one class of 7, melanocytic nevi, filling 67% of the space. This imbalance was a major complication. This plot shows that most of the melanocytic nevi data populates ages less than 55, whereas most of the age population for basal cell carcinoma, melanoma, actinic keratosis, and benign keratosis-like lesions range greater than or equal to 55. Filtering the data by age may be an opportunity to improve the melanoma score. The table to the right shows the change in ratio of melanoma to NV, which basically halves the influence from NV, which is, of course, melanocytic nevi. It does, however, reduce the data size by roughly 60%. In this example, we're looking at a comparison between the original 600 by 450 and the resized 160 by 120 images. To get a feel for the change in resolution, the size change is a 93% reduction in pixel count. The choice to use 160 by 20 was a compromise between speed, resolution, and compute limitations. The side-by-side image comparison shows some reduction in resolution, but it's really hard to tell. How much of an effect this had on accuracy is undetermined. Probably safe to assume accuracy would improve as the pixel count increases. Train test was split 80-20 and the remaining train set was split 87-13 train validation. Changing to an array was necessary because the CNN image classification requires the data be in an array. Standardizing, feature-wise standardization, that is, was chosen over normalization. Standardization is typically the preferred method for large color images. Standardization uses mean and standard deviation statistics, whereas normalization is a rescaling of pixel values by dividing by 255. Standardization across the train and test sets produces the properties of a standard normal distribution and centers around 0 with a standard deviation of 1. Converting to category cross entropy is required since the data is multi-class and color images need to be reshaped to 3 dimensions. A quick look at this test model shows an architecture that is very simple and basic and mostly provided here as an example starting point. These plots show the test model performance without and with data augmentation. It's clear that a deeper and more complex built model will be necessary. It's obvious from these plots that overfitting is going to be a big problem. The final model, Model 4, is one of 8 models attempted. Model 4 input included 160 by 120 3-channel images resized from 600 by 450. This final model included 9 convolutions in 4 groups, a 2-dense group, a flattened layer, and a dense layer, which is the output. For this presentation, we separated the input layer from group 1. Each of the 4 convolution groups included batch normalization, max pooling, and dropout. The kernel regularizer, L2, was added to the convolutions and dense layers, except for the output. Now these are the accuracy and loss plots. Combining batch normalization, max pooling, and dropout had helped improve the scores and reduce some of the overfitting. However, adding the kernel regularizer significantly reduced the overfit, but constrained the accuracy score a little bit. Looking at the plot, both training and validation seem to have peaked at around 42 epochs, but maintain a parallel path. However, it appears highly unlikely that the model would converge even if running extra epochs. Here we're going to look at model averages. This table shows 5 separate Model 4 runs and the averages for the CNN scores, AUX scores, and F1 scores for overall model accuracies, melanoma, and basal cell carcinoma. Although the model accuracy reached 80%, which was the target, an F1 average of 0.55 for melanoma was far from ideal. Most of the problem can be attributed to the imbalance covered previously. Earlier models showed that the data augmentation improved melanoma F1 scores by about 7%, which does not seem like much considering where it is now. Many runs with different augmentation values either showed no improvement or caused the model to behave badly. Increasing the class weights for minority classes, such as for melanoma, did not work at all. We'll be looking at model accuracy and classification report. We can see that for Model 4, run number 2, the CNN accuracy is 79.88% with a final loss of 0.97. The F1 accuracy at 80% looks pretty good considering the limitations previously covered. However, the problem is that accuracy is not a particularly good indicator of how well a model performs when the data is highly imbalanced and when there is a focus on a specific class in the minority. So, for the classification report, we will be looking at the melanoma F1 and the importance of exploiting the macro average. It's just going to be a quick coverage of the macro average. There are 2 co-conditions in which the macro average should be used instead of the overall accuracy when choosing between models. Those include when the data is highly imbalanced and when there is an emphasis on one or more underrepresented classes. Increasing the training through data augmentation did not have a significant effect on overall accuracy, but did help improve minority class scores. It is likely that the performance result could have been improved by using a larger sized image input, a much greater number of images available for training, and a larger compute capability to allow a deeper model build. Using a pre-trained transfer model, such as Inception or BGG, was not the intent of this exercise, but would likely have produced better results. Equalizing distributions, such as covered in Slide 8, may be the way to go sometime, possibly in the future. Thank you very much for watching this video. Have a good day, and this is the end. Bye.